to the SEG Europe Regional Advisory Committee's webinar series, State of the Energy Industry in Europe. Dr. Adriana Ramirez, Chair of the SEG Europe Regional Advisory Committee, and myself, Lori Weitzel, will serve as your host for today's webinar. Before we begin, the model for this webinar will be a short discussion, followed by an extended question and answer session. During the question and answer session, if you'd like to ask questions, please raise your hand in the webinar interface, and I will adjust your settings so you can ask your questions directly. Alternatively, if you would like, you can enter your questions in the question and answer box. Dr. Erik Larsen is co-founder and CEO of Earth Science Analytics, a company focusing on the commercial application of AI and data science in petroleum geoscience. He has 20 years experience from the exploration and production industry. He has held various technical and managerial roles in oil companies and consultancy firms, including Statoil, Rocksource, and Geoconsulting. He has experience from research, exploration, field development, and production on the Norway continental shelf, as well as internationally. He holds a PhD in petroleum geology from the University of Bergen and is now laser focused on implementation of AI in petroleum geoscience. Without further ado, please welcome Dr. Erik Larsen.
Thank you, Laurie.
Thank you for your introduction, Laurie. So, thank you for being here. It's a pleasure. So today we said we were going to talk about artificial intelligence, machine learning, data, etc. We have seen how these technologies have been disrupting other industries. The technologies are not foreign to us, but the big change is coming really, or is starting in the oil and gas industry. So that's what I would like to talk with you today. But before we go there, I would like you to say something about your background. It's not the most common background, I think.
Yeah, Laurie already mentioned a few points. What might be unusual is that in this space of digitalization, AI, machine learning, my background is as a sedimentologist. I worked most of my career in the oil industry with hydrocarbon exploration. So it might come as a surprise that somebody with that background is now focusing 100% on AI. So it's been a journey, and so I worked many years in exploration, and at the end of that part of my career, I was working as a consultant, trying to do a good job for the oil company that hired my services. And I had this realization that there's something missing. That in order to do best possible job, I realized there was a missing piece. Because a lot of what we do in exploration is to make predictions. And there are many different data types. We have the seismic, we have the well logs, we have core data, and the core data goes to laboratories where they measure porosity, saturation, petrography, hydrostratigraphy, and all of these pieces. We try to build models with those, and bring it all together to make a prediction of what is the range of volumes in some track. So it was at the end of a project when I realized that this phase of bringing it all together is complicated. Because by nature it requires you to do classification and regression mathematically based on multiple inputs.
Because there is a timeline.
And you're always working against the clock. But in this particular project, I had very long time to do the work, and I set out to do a really good job. I had 2 petrophysicists on the team. We had petrography from one of the great vendors in the UK. So all the data was there lined up. When it came to making the prediction, I just realized that I cannot do multi-dimensional regression with nonlinear systems in my head properly. So then
You have too much information to deal with at once.
Yes, so what I tried to do was I stayed late in the office and borrowed the boardroom of this company, huge table. So I took all the cross plots of this property against that, followed by this, and printed it out and laid all these prints around the table and tried to soak it all in. And you just realized that you cannot do it.
You were doing pattern recognition.
Yeah.
Regressions.
So that was a bit disappointing. After all this work, we had to resort to what we do when we're in a hurry, to just use judgment and massage it all together with some subjective expert opinion. So that triggered me to try to figure out, is there some other way to do this kind of thing? I assume that there are people smarter than me in the world who study statistics and so on. So they must have had this problem before and have probably come up with a solution. And so that journey into reading statistics and related topics led me into look at machine learning.
So it was a real life problem and a passion to
do better.
To do better that brought you here. That's quite interesting. And also I like the fact that you mentioned other industries, and because all of this has been tried and used in different ways by other industries, we of course have to have our own flavor. But for the benefit of our audience, can you say something about what you mean when you talk about artificial intelligence versus machine learning, deep learning? And where do you think we are as an industry? At what level?
Yeah, it's a bit philosophical, this whole concept of artificial intelligence. But I like to think of it as the ambition to build machines, robots, or computers that exhibit intelligent behavior similar to what humans do. So that's a long-term blue sky goal.
Yes.
to get there. And on the way, we need to do some practical. So that's where I think the term machine learning comes in. So machine learning is part of the solution, or current solution to artificial intelligence. And it is more tangible. So it comes in many flavors also, but what we will maybe discuss most here is the flavor that's called supervised learning, which in a superficial way is quite simple. So it just means that you have some measurements, which could be your seismic cubes or your wildland logs or photographies for that matter, and you have some ground truth.
Just a second. We're getting some feedback. Is somebody muted?
When you two are speaking, could you kind of face the computer? A little bit muffled.
Okay, we need to speak louder.
Yeah.
Sorry to interrupt.
Yeah, so we're talking about what is machine learning. So there are different kinds. The one I'd like to talk about is the supervised learning. So you need these pairs of some measurement and some representation of the ground truth. And in daily life, it can be photographies and then annotated kind of masks drawn on top of the photographies to identify the objects that are in there, the meeting tables, chairs, whiteboards, people. So when you present these pairs, the photography and those labels that we call them, to the machine learning model, the task for the machine learning model is to quantify the relationship between the two things in the pair. And so once that is quantified, you can take the model and subject it to new input, which would be new photographies, and out from that equation, if you like, comes the annotated masks. And so in geoscience, this could be seismic volumes to seismic interpretation.
Yes.
Or in petrophysics, it can be wireline logs to porosity curves or lithology logs.
So that actually brings us very easily to the topic of bias. When you are training your algorithm, there is an inherent bias in the labels that are created by humans, right? So that's one type of bias. And one type of bias that you also emphasized recently is the bias about data itself. Because you mentioned something about the course example, for example. Which one is larger? Maybe mention that story, perhaps.
Yeah, we need to be very mindful about the bias, not only when we work in machine learning, but also when we do geoscience in the traditional ways. And there is an example that I use a lot in talks with some statistics from the Norwegian continental shelf. So it was gathered by the Norwegian Petroleum Directorate. So they know all the pre-drill estimates for all the exploration wells.
Yes.
And they know all the post-drill volumetric calculations. So they published like anonymized chart where they compare pre-drill versus post-drill. And we see that in Norway, during the last 20 years, I think, we are overestimating the volume by a factor of 2.5. And so the UK authorities did the same and came to a very similar conclusion. They're overestimating the volumes by a factor of 2.6. And it seems that this is also a very systematic bias also in the US and I think anywhere around the world. So as explorationists, we have a very strong tendency to overestimate.
Yeah, it's also, I think the phase is also quite often overestimated in terms of the amount of oil versus gas that's expected in place. Usually oil is overestimated.
Yeah. So there can be many reasons for this, and I think explorationists are and perhaps need to be optimists by nature, because more often we are wrong than right in our predictions. And you need to persevere and keep going.
How can machine learning help here?
Yes. So that example with the overestimating of the volumes, this bias definitely does not come from the data. So it comes from some psychological factors, I think, and some political factors in the decision making. So what we are trying to do is to exploit a more data-driven approach and avoid the strong human biases. But then when we go there, we need to be mindful that the data that we're using itself is biased. So you asked about the core data. So if we train machine learning models to predict porosity curves in wells as a function of the core plug porosity measured in the laboratory, as a measure of the ground truth, and the wireline logs, we will train on a data set that comes from cored intervals. And cored intervals are where we have the cores, and the cores were taken there in the specific locations for a reason. And when do we take core? Typically when we hit the reservoir. So the reservoir rocks will be overrepresented in the data set, and the non-reservoir, especially the seals, sealing shales typically, will be underrepresented. So then, in order to mitigate this, we need to find ways to work around this data bias.
This is interesting because we often talk about the sheer volume of data that we have as an industry. Historical data, more than 100 years, the amount of data that we acquire every day, and the amount of data that we don't use. And at the same time, what you're saying is some of our data is also very deficient. I know very well in Seismic we have that problem. We have tons of data, but our measurements are so sparse, we cannot measure all around our interval of interest. So we have just by nature, from the beginning, an ill-posed problem. And that goes also into our assumptions that have to be put into the algorithms. So even our algorithms have a certain degree of bias. Is this something where machine learning can help? Is this something where physics can help? Physics has been a very good ally for us. How do we mix this? How do you envision this part?
Yes, a very good topic to discuss. And so lots of what we are doing and can do in AI and geoscience, we can do by transferring technology from other domains where it is already mature and successful. But there are some special features with the geoscience data that it's very large. There's petabytes of seismic around, thousands, millions of wells. So it's very large data, but it is very sparse. So the wells are more or less point measurements, and the seismic is sparse in the form that it has this limited frequency content. So we have always known that our problems are ill-posed. Also when we solve the problems with physics and with geology. So we have some solutions to this. And we have been addressing our problems by illuminating them with the uncertainties. We're making predictions with uncertainty. So it's absolutely necessary. And this is nothing new. In the volumetric calculations, we typically have used the Monte Carlo simulation to get the range of the in-place volume. And we can continue doing that. But the way we did this in the past, you need to input to the Monte Carlo simulation some property distributions, like the distribution of your gross rock volume, the distribution of your porosity, distribution of your net to gross, the formation volume factor, and the saturation. And each of these distributions kind of always came from the data, but they were kind of traveled through some expert, and the shape of the distribution
so we go back to the human
was
bias.
very much subjective.
Yeah.
And is in most cases also today. But it is rooted in the data. So the question is, can we make these distributions that are input into the Monte Carlo simulation more data-driven? And we think we can. So then we can apply machine learning models to compute each of those distributions, and then do the Monte Carlo simulation. But then we need many machine learning models, one for each property. And each machine learning model needs to be able to make a prediction with uncertainty. So it's not a scalar, it's not a single number, but it is the distribution.
And you have to train that code as well, right?
You have to train these models on your measured data and on the representation of your ground truth. So I think that might be something where we need to be creative in geoscience. So it's not just taking computer vision algorithms and applying. We need to tailor make some methods for our own domain. So we have done this for seismic interpretation, for example. So two interpreters will not make the exact same interpretation. But if you had the luxury of employing 1,000 interpreters to interpret one horizon, maybe you could optically stack them and extract the mean, plus minus uncertainty bands.
Yes.
And you would have something better to use in your decision making. But you can't afford to pay for 1,000 interpreters to interpret every single horizon. But the neural networks, they don't get paid, so you can exploit them to do it.
But
So,
to train them, do you train them only with experts? Do you train them with modeling? How do you best train them?
so for seismic interpretation, which seems to be one of the more mature applications of machine learning in geoscience, we can train in multiple ways. So you can train on expert annotations or labels, and we call it in machine learning speak,
Interpreter?
which is just seismic interpretation. So you have a bunch of seismic interpreters to interpret a lot of seismic volumes. And then you have these pairs that are needed for supervised learning, the ground truth, which is the interpretation, and the seismic volume itself, which is your so-called feature set. And that's what you need to start training these models. But there is another method that you can also use. You can train on synthetic data.
So using physics to model data?
Yeah.
Okay.
So you can have some tools that will generate Earth models for you with the elastic properties and all that. And from these Earth models, you can compute the synthetic seismic with lots of different frequency content, wavelengths, and so on. So then you have a faster way of building your training sets. But you get the same. You get the ground truth and you get the seismic data. We
met at a conference recently, and there were, I think, about 8 different presentations on this topic in particular. It's a hot topic. It's a low-hanging fruit. It's an easy application. Well, maybe I should not say easy, but it's one of the first applications that comes to mind. And one of the back to machine learning, one of the general comments are, what if the machine is wrong, right? So what if they give me the wrong answer and I just follow it blindly? But in this topic that is automated seismic interpretation, getting some maturity, are we at the level where the machine can outsmart us, or are we still having to check and tell the machine that it's not completely accurate? At what level are we?
The seismic interpretation tools using AI are getting quite mature now, but they are mainly living in R&D teams of technology companies.
So we're not ready to bring it into production.
So they have not at a big scale been deployed in the exploration teams and the field development teams and so on. But this is going to happen very soon, I think, because now we're seeing that these tools are moving beyond R&D and we're seeing products emerging. And that's what we do in our company. We build products for the users that the generalist geoscientists can use in their daily work.
But are these tools at a level where I can provide some interpretation, maybe not everywhere, in some areas, and can the machine correct my own interpretation? Or besides adding in the areas where I didn't touch the data?
Yeah, so these tools enable you to, also here there are many approaches, but the one that we see most often in conferences is the one where the interpreter interprets some seismic lines, and then that becomes the ground truth. Yeah. And the deep neural network, the convolutional neural network, trains on that seismic cube versus annotation pair, and produces a result that is then fed back to the user. So you can look at that result and judge whether you need to provide more labels or if you're happy. So typically you need to provide some more labels where you have some difficult issues, and you can run it again. But that cycle is kind of slow because you need to label a bunch of seismic lines, but not necessarily that many, like 20 is typically enough. But then you need to train the thing and get the inference and judge it. So a more useful approach is to have some pre-trained network for a specific task. For example, fault interpretation. And you just activate that network on the cube that you're working with. Yeah. You get the inference of the prediction. So the interpretation appears on your screen. So now you can judge the quality of this, and you will see the shortcomings. So maybe you need to add some fault here, delete some fault here. That was not really a fault, it was the margin of a channel. And that limited input that you're getting is fed back into the network. So it retrains and it immediately provides a new prediction on your screen. So now this cycle of improvement by adding layers, labels for interpretation is much faster. So
we can expect, of course, adoption is one of the problems. We are a very traditional type of industry. It takes time to move into new ideas, but nowadays we need to go faster and embrace change.
Yeah.
And I think that's also, for example, interpretation. It has to be a moving target, right? In the sense that this is the best we can do today, and as you keep training your algorithms and getting more information, you should be able to produce better and better results for the same data.
Yeah, and we see that this is really working, and it's going to be a game changer for seismic interpretation. Because the turnaround cycle with this approach is so short, it's hours compared to days or weeks to interpret faults. So tasks like that, I'm absolutely sure that these will be, like in this example, they will be semi-automated. So there will be some human input to optimize the models, but it's very limited of input that is required. And then maybe going forward, because these models will improve every time somebody adds input, so that pre-trained model that runs in the background will get better and better every time an interpreter interacts with it. So at some point down the line, it will produce pretty good interpretation at the first time you apply that model.
So I want to talk a little bit more about the value proposition of machine learning and the digitalization. We have touched upon speed and some of the low-hanging fruits. What other values do you, if you have to name three, the potential of just three aspects?
Yeah, so the obvious one is speed, efficiency. But we also need to have greater goals, and these other goals is why I came into this domain in the first place. So we want to do better predictions. So we want to understand uncertainty better. We want to quantify uncertainty as a function of all the data we've got, just being able to use all the data. We also want to use AI for knowledge discovery, and not just for automating things that we can do manually.
What do you mean by knowledge discovery?
So we could say in supervised learning that we talked about, you're using these pairs of interpretation versus the data, and you're getting a model that can automate this process and generate new interpretation. So in a way, you're getting more of the same. But it's, of course, happening at the scale that allows you to be like 100 times more efficient. So it has a huge value, and it's part of reducing the time from getting access to new acreage to first oil. So there's a huge profit to gain from that alone. But also, I'd like it to see methods where you can, that will kind of fuel our creativity and cover things that you otherwise wouldn't have seen in the seismic data, for example. That kind of brings my thoughts onto unsupervised learning, which is currently not adding so much value, but we will slowly get there, I think. So, and we have clustering algorithms, and we've been using this in geophysics for a long time, where we did nationality reduction, k-means clustering, and all these things. And now there are more modern ways of doing this. And those methods have the possibility to identify patterns in the data that you wouldn't see if you just looked at the raw data.
So, yeah.
And that can be very inspiring for an explorationist, because the whole mindset of an explorationist is to look at the data, be creative, and to get some feedback through this unsupervised learning approach.
So you're thinking about things like self-organized maps and pattern recognition, so that then you bring the human or other tools and look into this, what the computer has highlighted as of interest.
Yeah, we do see some commercial applications of this already.
I think it's starting
I think there's a huge scope to modernize those approaches and use the convolutional neural networks and build a kind of next generation of these tools.
Yes, I agree. I have seen a lot as well, and some of them my concern sometimes, and I'm a physicist by training, so my concern sometimes is that people want to read too much into some of these maps or patterns. And we want to find more of it. That's why we're here, right? So sometimes we have such a passion and interest to succeed that we don't stop back and really question, especially this kind of algorithms that sometimes are more of a black box. That's my only concern with the hype, that something works in one data set. It doesn't mean, especially on supervised algorithms, it doesn't mean it's going to work everywhere. Not yet, I'll say.
And that makes me think of integration. So integration is the key word for what we do in our company. It's been a buzzword as long as I can remember.
Yes.
But now we can do it in a different way. We have all the data types. We have the ground truth from the core, we have the fluid samples, we have the oil analysis, and we have the seismic. And we're going to come up with 3D volumetric estimates with uncertainty. So let's say that's the job.
Okay.
So the unsupervised learning methods have this problem that they just tell you if this box in the seismic belongs to this or that class. It doesn't tell you what exactly it is in geological terms.
Mm-hmm.
But you do have this other data. So you can map the relationship between your classes from the clustering and the ground truth from the WAPs. So it means that you need the system that allows the seismic tools to speak to your well tools and align these things in 3 dimensions. So
yeah, and I like that, because that's actually using some of our strengths. As an industry, we have been very focused on algorithms, physics, geology, trying to bring as much as we can for this hard problem. And we know what the strengths are for the different data sets, and we can play that in that integration.
yes.
Analytics to integrate it. And we just, we still have a little bit of time, so sorry.
In order to make this integration work, something I'd like to highlight is, so you need these tools or the software to do each task. So you need software to do the seismic interpretation, to interpret all the things that you need to interpret: the horizons, the faults, the geobodies, the channels, the salts, all that. And you need another set of algorithms that interpret the porosity, the lithology, the saturation in your wells. So you need to combine this stuff in order to get to volumetrics, including uncertainty. So it's a difficult task. It's a huge task.
Yeah.
And there is one element that is absolutely needed in order to succeed, and that is to build these platforms where these individual applications are run, and where the data is hosted, and where your supercomputers in the cloud can be accessed. That
brings us to a topic we have not touched upon, and before we open up for questions, I would like to get your view on cloud and code.
Yeah, so the solution we in our science analytics are using is cloud. So in the cloud just means that it is a server somewhere else. It's not a workstation under your desk. But we use these cloud providers such as Amazon, Microsoft Azure, and Google Cloud Platform. And there you can host your data, and you can access the supercomputers. And it gives you scalability as well, right? It gives you scalability, and a small company like us can access a supercomputer. Any user of the software has access to a supercomputer.
So this is giving a democratization of technology, one way or another.
Yeah. So on these platforms, every user has access to a supercomputer. Every user has access to all the data, all the seismic, all the well logs, all the core data, all the fluid samples. And on the platform, there are all these software modules that solves the individual problems. And then we need to do the integration to make these applications speak together to solve the complex higher level problems. At each step on the way, we need to make our predictions, including uncertainty. so that uncertainty is aggregated into the final volumetric result. Instead of, like in the past, at least from my experience, dealing with uncertainty was something we did at the end of the project. And therefore it was highly subjective, instead of making it data-driven all the way through.
Yeah, and uncertainty is something we're not very good at least in my part, more towards the seismic part and data measurements and processing.
Yeah.
We have the means to measure uncertainties, but we don't do it quite often. We don't track them until later in the chain.
No, and we should address it at every step. I'm from the exploration background, so I talk about things colored by my background.
Of course.
So in your background, and now we are in the meeting room of a seismic company. So you can track the uncertainty all the way from acquisition. So there's uncertainty in migration. So where the riggles appear to be on your slice is not necessarily where they are. You can have many realizations of that. And addressing uncertainty at that level is very rare to see for the generalist when we do webinar.
Yeah, I think it was Jonathan who mentioned that, yeah, we can get some more uncertainties for our migrations and inversions. Then that means that we have to take more time to calculate uncertainties. And instead, his proposition, and probably one way or another what we have embraced, is instead of calculating that, let's just compute more and get to another iteration, right? I'm not saying it's the right way of doing it, but one of the things that I do see from analytics is that it's almost a byproduct to have uncertainty. So the more we embrace this route, the better we're going to become as an industry, I think.
Yeah, I think it's absolutely key. So it addresses the facts that we have sparse data sets, although they are large.
Yes.
It addresses the fact that we have ill-posed problems. So providing predictions with uncertainty that are data-driven all the way through, it just seems like the obvious thing to do.
Yes. Let's open for questions and answers, and then we can come back to a couple of extra questions that I have for you. Lauren, do we have any questions?
Yes, we have a question in the question and answer box, and it says, how do we ensure the uniformity of data quality, velocity anomalies, lateral variations, and non-homogeneous and processing bias in training and application data set, meaning seismic and well log data? And what are the tools that we currently have to ensure them?
Okay, so I'm interpreting the question a bit, but I've heard similar question a lot of times. Our measurements are from different tools. The environment of the measurement varies. So,
like the uncertainties of each measurement plus the granularity.
Yeah, so in petrophysics they do environment correction before they do their physics to compute the curves. And there are different tools in old wells versus new wells. So it sounds like machine learning wouldn't work when you mix all this stuff. But we have done experiments to address this, and it turns out that when your data set is very large, and you have many examples from each logging tool, and many examples of different drilling fluids with different densities and salinities, the models are able to generalize across this variability.
Compensate for it.
And compensate for it, because the models can deal with these complexities when they're trained on very large data sets. So there is...
So that's some of the unlocking of the value amount of data that we have.
Yes. So you could see and think of an analog in photographies. Like we see that these computer vision systems, they can identify cats easily. It doesn't matter where the cat is looking, if it's upside down or curled together like a ball. It sees that it is a cat. It doesn't have to look like the typical cat of a cartoon. So it generalizes. Because during the training, it was subjected to a high diversity of training examples.
Lori, we cannot hear you.
Okay, could you indicate the most useful open source software in machine learning for solving geophysical issues like reservoir characterization, etc.? Also, how useful are other methods like adversarial NN compared to CNN?
There's so many useful libraries and open source tools. We as a company, we are a software provider. We build heavily on source. So for machine learning algorithms, also we use Python as a language. We use the machine learning tools from Google, TensorFlow, we have Keras. So there's a jungle of these libraries out there, and we use them widely. That's not to say most important.
Yeah.
The second question, I didn't quite get that.
It was not.
Yeah, they were curious how useful are other methods like NN compared to CNN?
Yeah. No, we see. I think this adversarial networks are interesting, and a lot of interesting stuff is happening in R&D. Currently, we're adding the most value the like currently supervised learning ones with like fully convolutional networks. But the so-called GANs, or generative adversarial networks, I think they were invented kind of to generate like artificial examples that are mimicking real ones. So there is some promise of building training data that way. So I think that was the original intention from Ian Goodfellow when he came up with the idea in the bar in San Francisco some years ago, that this is a way to mitigate this problem of not having enough training data. But now we see that field is blooming. We see that you can build generative art that looks realistic. You see videos on Twitter that they get Mona Lisa to turn her head and smile and talk.
I mean, you can write papers that get accepted.
Yes.
Unfortunately.
At least you can have Twitter bots and fake Donald Trumps and all that. So it will be interesting to see what will be the kind of valuable geoscience tools from this. But I think it will find its place. Maybe in geomodeling, the geocellular modeling. So we've been used to using stochastic modeling of bodies like channels, fans, by sampling from distribution of widths and thicknesses and sinuosity and all that. A process like that can be replaced by generative adversarial networks.
Yeah.
To generate realistic geology that is not necessarily in the right place in the subsurface, but the shapes are realistic. And you can generate a bunch of these and then assess some certainty on top of that.
Yeah, I mean, I can see it a little bit for scenario testing, for example.
Yeah.
Just to update certain shapes and test it with your data. Do we have more questions?
Yep. We have a question that says, it's a two-part question, I think. What kind of example would you try in a mature oil field? And then also sometimes to develop regression models that predicts another log curve from other LSTM, long short-term memory, has better results. Is this true?
Yeah, two questions. In mature fields, I did work in production for 1 year on the mature field, and a lot of the focus is on identifying unswept oil and to plan to drill injectors and producers in order to sweep the remaining oil. So obviously then you need to predict where it is, where you have poor sweep. And 4D seismic comes in there if your reservoir is detectable by those changes in the seismic. So we have these workflows already, the time-lapse seismic, but with machine learning, something that we do in our company is to predict rock and fluid properties from seismic. So it's kind of an inversion approach, but we do it in this one step from the partial stack seismic and directly to the rock or fluid property that we care about. So you don't have
to train an algorithm for this, or
yes. So you do not necessarily have to go via the elastic properties. You can go direct. And the way we train these models is to align the seismic with the known properties from the well. So you need to make sure that your well tie is near perfect, that your deviation curve is near perfect. So you have the feature label set perfectly lined up. And then we see that we can make this direct leap from your offset seismic and directly to the properties. And this you could repeat on each of the vintages of your 4D, and then you have like you can animate the sweep basically in some discrete steps at least.
It's quite interesting.
And the other question was, can you predict curves from wells and RPM better? So we do routinely predict curves in wells, and these what is called the classical machine learning methods like random forests and other ensemble methods work really well to predict porosity, lithology, saturation, etc. But we see that there are examples that you can have some extra improvements by using LSTMs and one-dimensional convolutional neural networks, and you can also build LSTMs that also include these convolutional filters, because these networks will not only see the value of the logs versus the ground truth, like row by row, but they will see the succession of measurements up and down the well. And that's something that's intuitively makes sense for me that it works, because as a geologist, when I look at well logs, what catches my eye immediately are the trends. So I see from the gamma ray coarsening upwards, it's a short phase. See the bell-shaped binding upwards, it's a trivial channel point bar. So it makes perfect sense to me to exploit the vertical patterns. And so when these CNNs and LSTMs can do that, versus the row-by-row methods do not, unless you capture it through your feature engineer, which you can also do. But that kind of mimics the same thing as the LSTMs do. So applying just these traditional methods gets you a long way, and it's much simpler.
Okay, we have several questions. As supervised learning uses previous cases, don't we run the danger to ignore new approaches? And what do you do to prevent that from happening?
Yeah, that's a good one. And it's true. And it's something we need to deal with. And we highlighted this goal of knowledge discovery. It's something we want to achieve. And we need to work on. Because the nature of exploration is that we need to find something that we previously didn't know about. Otherwise, it would be discovered already.
Especially mature fields. So yeah. 90% of new oil is usually found in immature basins. So. Yeah.
And so it's this conundrum. Like, can supervised learning or machine learning in general predict the black swans, things we have never seen. So it sounds like it's not a supervised learning approach, because you cannot train a model with ground truth and measurement pairs when you have never seen this form of the ground truth.
You're asking any questions to the machine.
So, but in supervised learning, certainly you can apply these methods, and this new thing will appear as some cluster, but it won't tell you what it is. So I think that's something we need to work on, and there's not a lot of examples of this, although we see some. We see some in seismic interpretation.
So there's potential.
There's great potential for the future.
Okay. Software programming skills are very important for professionals these days. There has been a big push for Python with the digital agenda. Why is this? And do you agree that Python is the enabler or the right program?
Yeah, I think it's great that the oil and gas companies and also technology providers are encouraging their staff to learn to code. So myself, I'm not a great coder. I can write some code, but as we're developing software, obviously we leave the coding to professional trained computer scientists who collaborate with geoscientists to build the tools of the future together. But having this, at least some basic understanding of programming and the logic is a really good background for any geoscientists. And for those who pursue it further than the basics, it's a super valuable tool because it gives you full freedom to build anything you like. And we see innovations happening from geoscientists that are reasonably good coders who use their creativity, and they can code prototypes themselves and get them out there, and they share it, and it just evolves in the network. So one person is inspired by the other, and it grows. Especially now that people share so much on GitHub and open source. The community spirit and inspiration really makes things progress. And in terms of Python, it is the main language used for machine learning because these popular machine learning libraries are based on Python, but there are also others.
But I would say also Python has a lower entry point than C++ or Fortran. So it's much faster to start coding and to understand what you're doing. That helps a lot, I think, to bring everybody into this area.
Yeah. So in order to have meaningful, fast progress, we need to build upon what others have done. So we need to use these libraries. We need to be inspired by other people's work. So I think people are not building these things from scratch anymore, although you can if you're an expert in some fundamental language. You just fall behind.
Okay, I'm going to follow up with that question because at one point early on in your response, you mentioned a few places where people are sharing codes, like Interp, and another place. And I don't think that I heard it, and if I didn't hear it, probably our audience didn't either.
Yeah, there's something called GitHub. So a lot of scientists also have their repositories there, where they share their experiments and their prototypes. And also several of the oil companies are contributing and sharing code there, like the big oil company in Norway, Equinor, is sharing Segway readers and very useful tools that allow young geoscientists to rapidly start building code for Seismic because they don't have to build the Segway reader themselves. They can just take it from there and build upon it. So there's, and we see it also from the tech companies, Google and many others are Facebook, and many companies are sharing their libraries. And because of this sharing, we see this rapid development. Everyone doesn't have to build everything from scratch.
And maybe there's more possibility of getting new ideas, fresh ideas.
Yes. And Uber was the one I was going to mention. It's, they are kind of a taxi company, but they have a huge AI team. They're publishing lots of nice open source tools for geospatial analytics and AI.
Okay, we have a question that I guess builds on this conversation about Python. It said, why should we all know Python? Very few know Fortran, C++, Java, etc. Why not make user-friendly software instead?
Friendly software.
Yeah, I think it's good to have a fundamental understanding of what programming is and what it can do. But for the masses of geoscientists, for most of the generalists, I predict that also in the future, these people will be using software that has an interface that is connected to a data platform, and they interact with it through this user interface. So they do not write the code themselves. Because if everyone is going to do their work by applying their Jupyter notebooks to solve this and that, we're going to generate a big mess in the data management. There will be CSV files and stuff floating all over the place. So for companies, we need to keep some order in the house to have these data platforms where things, different data types have the place where they reside, and the output comes into the right place, and the applications can consume them from there. But still, in order to have this innovation going, having geoscientists experiment in Jupyter notebooks, which is Python, that's a great benefit. So.
I think it's also about, I mean, if you're, at least in my side of this field, it's good to fail fast with new ideas and be able to test concepts fast, preferably all the way to real data. So having an interface that allows you to code and plug in small codes just for testing, that is a safe interface, so you don't mess the rest of it. Yeah. It's good, because then you can generate more ideas, you can evolve fast, and then actually implement it properly.
Yes. We will see that these data platforms, as they become more in mainstream use in the old companies, they will have APIs.
Or microservices.
Yeah. So the provider of the platform has taken care of keeping order in the house and data management and access to supercomputers and all that. And then some geoscientists who have some creative idea can plug in their scripts and run it in this environment. And that takes away a lot of this hard work that the geoscientists otherwise would have to deal with.
Okay, we have more questions. Coming back to a previous question, do you think that machine learning tends to prevent thinking outside the box? As usually we look for anomalies in the data.
My view is that the opposite. That it allows us to do completely new things that a few years ago we would never have thought of. So it opens up big changes. We're seeing these changes all the time. Next month, I'm going to a hackathon with a bunch of geoscientists here in Norway, and I'm absolutely sure some of these teams will produce prototype applications that do something that we never thought about before. And they come up with it in a matter of 2 days of coding and build a prototype. So this trend that we're in now will definitely keep us thinking outside the box and think Francesco Ortigosa or Repsol said it nicely that we are realizing now that there is no box. So it's just opportunities, and everything will change at a much faster pace than it has done in the past. And we'll see like an explosive innovation. Partly because the subject matter experts, the geoscientists, are driving it. So this innovation is not something that happens only from computer scientists, but it is driven by people who want to solve their problems in better ways.
More tools to play.
Okay. We have a question. How much time, computing resources, storage infrastructure is required for any given volume of data? Seems like a hard question.
Yeah.
Maybe the next one.
One comment is that if you are an individual and you want to experiment with these things, you get a long way with a laptop. You can experiment with small problems and be creative and build useful stuff. But when we scale to build tools that are meant to solve industry problems, sometimes we need access to a lot of storage for the very large seismic data sets that exist today, and also to a lot of compute. And luckily, we have the cloud that gives us access to this to anybody. So anybody with an account with a cloud provider can access a supercomputer with lots of GPUs.
But I mean, that I agree with you, but I also think access to the data, fast access to the data is also important. And that's not completely solved, but we're getting better at it. And there's also initiatives for technology that will enable what it's called nowadays microservices, where given company can open up certain data to certain individuals to play with it or to work on it or test an idea. But that's still something I believe we're working on.
Yeah, there is more and more data, and also the large seismic volumes are accessible to the public. In Norway, we're lucky we have a national data repository where all the cubes are released after some time limit, and same to the wells. But also you have to be a member of this, but there's like a symbolic.
Yeah, I'm thinking for like student or
for students,
it's not that easy.
students it's too expensive,
Yes.
but for startup companies it's manageable. But for students, there is a growing catalog of open seismic data sets that you can just download from the internet. The New Zealand Mineral Division or something have opened up all their seismic volumes. In the Netherlands, with UK, it's opening up. So you'll have plenty of seismic data and also well data to experiment with.
Okay, building from that, what would you recommend a student focus on, assuming that the student is already studying geology or geophysics?
No, I think that is the topic of the day, this digital transformation and what's happening with AI and machine learning. It is part of the present. It's going to be even more part of the future. So if I was a geoscience student now, I would just get going and start to learn this. And there are lots of courses online. Many of them are free. You can do them on Coursera, online, or many other providers. And team up with other people working with similar things to be part of a community. There are online communities for this. Software Underground is one of them. It's a nice Slack channel where you can discuss with like-minded people. and join these hackathons and code sprints. So there's lots of opportunities to get together with other people who are on the learning curve.
It's a community, is a big, I mean, this growing community is quite relevant to get in.
Yes, and there are get-togethers and hackathons many times a year in many countries and cities around the world.
Okay, so I guess continuing this discussion, the question we have is how challenging would it be for a petroleum geology student to transform themselves with machine learning and artificial intelligence data science skills for the upcoming digital transformation of oil companies for their career and job point of view? So how challenging, what amount of lift would be needed to convert a typical geologist?
I think if you do one of the introduction to machine learning courses online, which is part lectures and statistics and the mathematics behind the methods, and part coding exercises that you have to submit. These courses you can do if you have a lot of time available. You can complete them in a few weeks, but if you do them part-time, a few months. Once you've gone through that basic introduction course, you have a lot of that background that makes you understand how this works. And then you can move on with some deep learning specialization or something that would be required if you want to go into like seismic interpretation and inversion type problems. You get a very good understanding from these introductory courses, and they are free, and I've done a few of them part-time. And we need to do that also, the students, the young professionals, and also those of us who have been around longer. We need to realize that we live in this time of rapid change, so we just need to keep learning like all the time. So you can't be in the mid-40s like me and live on the fact that I did a PhD in 20 years ago. So our knowledge needs to kind of grow and change with the times.
And embracing change.
Embrace change.
And you mentioned you have to enjoy change if you want to be in this.
And I think it's super exciting with this change. So it's not something to be afraid of. It's just something to jump onto and be a part of the ride. And it's super exciting.
Okay, great. Yes, and I think lifelong learning is really important for people who want to stay active and enhance their skill set. So we have another question, and it says, we have a huge amount of data in the industry and a huge variety of that data. But are there types of subsurface data that we should use more?
Yeah, absolutely. And for many of us, there are types of subsurface data that we would like to use more, but are not available in the public.
Like?
So, like we are in my company, we're doing an R&D project sponsored by some oil companies. So we have access through them to pre-stack gatherers and partial stacks and so on, combined with the ground truth proprietary wells that go with them. So we can work on that, but we don't find that laying around the internet.
So you want the integrated data and the label and interpretation derivatives, etc.
Yes, and when we met in Austin, we were talking about a data set that Equinor provided, and that's available online. And it has seismic and it has interpretation. So you have the seismic and label pair, so you can work with, which is good to start experimenting. And you can download it for free. I think the license allows you to do whatever you want with it, some commercial limitations.
Yeah, it's a Creative Commons license,
yeah.
But on the other hand, these, I was excited about this data because it contains not only the data, the measurements and the derivatives, like the seismic cubes, whatever was derived from that original data, but also the models that are the human part, the reports, and it contains all the biases and all the work of a field over the years.
So that we'll surely see talks at conferences more and more that working with production data together with time-lapse seismic data and multiple realizations of the geocellular models. So more integration of different data types, I think that's what we will see going forward. Yeah,
and I mean, actually, the topic that we just came into, this topic of open data, was very much debated in the conference, in the Energy Data Conference in June. And it's not in the sense of we want all the data to be open, that doesn't make sense. It's really from the point of view, we need certain data sets as complete as possible to be open so that we can have standards and we can test ourselves against each other and against truth or an understanding already existing.
Yeah, so that's absolutely true. We need some of these benchmark data sets that are strong in terms of ground truth, so that when I apply one of our interpretation models on this data set, I can score it with metrics against this ground truth, assuming that it is true.
Yeah, there's always bias. That's the reason I left.
and you can do yours, and we can kind of compare, and we will see what is the model of the month.
Yes. So I think this is a topic we will keep hearing more and more, and hopefully at some moment we will have industry benchmarks that we agree on.
There are some small ones out there. So someone published a seismic interpretation set for this famous F3 survey in the Netherlands. So you can try your own seismic interpretation code against that and compare it with your buddy's code and see who's the best. And for the Volvo data set that we talked about, there is the interpretation. But then just be mindful that the interpretation that is in that data set was built for another purpose. It wasn't built to be a label set to be used in machine learning.
Yeah.
So I think we need some more of those benchmarks.
Yeah, I think we're getting
there.
Yeah. Okay, well, we're slowly running out of time. Well, quickly running out of time. So, change the questions a tiny bit and talk about your experience as an entrepreneur. Can you tell us a little bit about your experience and creating your own path?
Yes, we already went through my CD, so I don't have to repeat that. But the first time I started a company was a consultancy company, one-person consultancy company just selling expert hours. So that's an easy entry into entrepreneur world. And the next step was to team up with other consultants, and we built a consultancy that we own together to sell our time under this umbrella company. But now when we started this data analytics company, Earth Science Analytics, that has been a totally different game. Because we're not selling hours anymore. We're selling software. So that has been quite a journey. And starting back in 2016, traveling around mainly Norway to pitch these ideas. I think many of our old friends thought we had lost our minds, believing in what we see today is now reality. So it was a struggle to convince people to do projects with us to support our R&D in the beginning. But having been in the industry many years, we had the ability to work on the software without paying ourselves for a while. So once we had working prototypes to bring into client meetings, that changed the game. Now you're not just presenting a PowerPoint slide deck, making claims about some future reality, but you're showing it live in the meeting, so people believe in it.
Some people underestimate the time that it takes to go from that idea, that pitch, elevator talk, to that first meeting with something tangible. What's that? 2 years, 2 years?
2016 was really hard, but then 2017, in the beginning of 2017, and until then, it's been accelerating. And now, digital AI, machine learning is on the list of every conference. It's everywhere. So it's been an explosive change. Yeah, it's been a journey, and you just have to keep making money on the way to sustain the economy of the company. Keep a lookout for these big goals, what you're going to build in the future. So you have to split your time building things that can be sold to get income, and building the things, the tools of the future that will bring you the future income. So this journey is not something that's going to end anytime soon. We just see the start of it. We see this AI petrophysics methods, we see the AI seismic interpretation methods, the AI immersion methods are maturing and they're becoming products. And in 2020, I think, will be a year of much wider deployment of these products into the oil and gas companies. But then we need to be working hard on the next generation problems and tools and products. And we elaborated a bit on that. Now we have these fundamental tools that do one task at a time. But we said that we need to integrate these tools, and we are starting to do that and building kind of a tier above that are consuming different types of data, combining multiple machine learning problems to solve a higher level task. And as we stack these things on top of each other, we're getting closer and closer to this concept of AI. It will feel more like something that is intelligent rather than just a classification or regression algorithm.
Okay, I think we have time for one more question. We could probably take questions all day, but we have to end eventually. Although I would personally like to just stay and keep asking questions. But our last question of the day would be, have new ways of working, such as Agile, helped your company to innovate and grow? Should geoscientists try working in new ways?
Yes, so absolutely, and it's definitely key to success in a small company, entrepreneurial companies. You have to be fast. We're competing with giants with 100 times more resources, so you just have to be creative, use agile methods, collaborate well. Have the sprints, build prototypes, fail fast, build the next thing that's better. But still keep an eye on the commercial side of things, keep making money on the way so that you can sustain the activity.
All right, well, thank you, Eric, and thank all of you for attending the SEG Europe Regional Advisory Committee's webinar as part of our webinar series, State of the Energy Industry in Europe. Please look for our social media posts to register for next month's interesting presentation. Thank you again for attending, and thank you, Eric and Adriana. Great conversation, and until next time, have a great day.
Thank you.
Thank you for having me. Thank you.
You're welcome.